This video is about Charles's Law and how we can think of the Charles's Law from an experimental perspective and also from the kinetic molecular theory of gases in terms of how we conceptualize it in our head so that we don't have to memorize everything. So first of all, let me remind you that Charles's Law is this. It states that when you increase the temperature of a gas, its volume will also increase. And when you decrease the temperature of a gas, its volume will also decrease. And obviously, because we are looking at T and V, and again, there are 4 quantities, we have to keep the other 2 quantities constant. So we have to keep the number of particles constant and also the pressure constant. So let us look at an animation now. This is the container, and let's pump in some gas particles inside. Okay, and then let's wait for it to wait for the particles to spread out all through the area, all through the volume inside the container, like that. And then now I have to check pressure here, meaning I will hold the pressure constant, because remember, in Charles's Law, we hold the pressure and the number of particles constant. Again, the number of particles, no problem, because if you look at this animation, see, the number of particles are inside. They can't go out. So you can't add any particles. You can't take out any particles. So obviously, the number of particles inside are already constant. So it's already implied that the N is constant. So now I have to check P so that P will be constant. Now, let's notice what are the values here. So you have the temperature is 300 Kelvin. So let's write that down. The temperature is 300 Kelvin. And the volume, again, in the volume here, there's no measurement, but let's just call this as 1 meter cube. Again, for simplicity, this is 1 meter cube, right? So that is 1 meter cube. And then what we can do is we can increase the temperature up to, let's say, 400 Kelvin. And let's observe what happens. Let's do that. 1, 2, 3, go. I'll heat it up. Now it's increasing to 400 Kelvin. Stop. So that's around 400 Kelvin. Obviously, that's more than what I intended to. But notice what happened to the volume. The volume increased. Right? The volume increased. And if I get it back to 300 degrees Celsius, so I'll cool it down like this. 300 degrees Celsius, cool it down. There. It returns to this one. Okay? So, what just happened? Well, what happened was when I increased the temperature to around 400 Kelvin, the volume kind of went into around 1.33 Kelvin, 1.33 meter cube, but it increased, right? It increased, and in fact, sorry, 1.25 meter cube. How do I know that? Well, I know because of the math, because I know that 300 to 400, you must get 1 to, so basically you divide it by 3 and multiply by 4. So you have to divide it by 3 and multiply by 4. So yes, the original calculation was correct, which is 1.33 meter cube. But again, the value doesn't really matter. What matters is if you look at this, if I increase the heat to, I hope you can see this. I increase the heat to 400 Kelvin. 1, 2, 3, 4. Let's stop. 400 Kelvin. Notice that the original volume was kind of like this here. Now it's like 1/3 bigger. It's 1/3 bigger than the original size, right? So it's true that when you increase the temperature, the volume increases. And when you decrease the temperature, let's do that. You decrease it to 300 again, like so. Then the volume also decreases. And again, the thing is, there's a mathematical equivalent for that. So if you notice, to get from 300 to 400, you have to multiply that by 1.33, right? So 300 times 1.33 is 400. So that means you also do that to the volume. So 1 meter cube multiplied by 1.33 is also 1.33 meter cube. So this is the idea And that is kind of the experimental result. Again, let me reiterate. If I heat it up, the volume increases. If I cool it down, the volume decreases. Heat up, volume increases. Cool down, volume decreases. So it is, again, very typical. I mean, very explanatory here. If the temperature increases, the volume increases. If the temperature goes down, the volume goes down. Okay? So that's the idea for the experimental the experimental side of explaining why the Charles Law works. Now, again, I'd like to give you a conceptual approach also. And the conceptual approach is, okay, why is it that if the temperature is increased, the volume also increases? And why is it that if you cool down, the pressure, the volume also cools down? Okay, so this is now purely conceptual. So the idea here is this: when you have a gas, right, and this volume can change, so it can shrink, it can expand, what happens is there's pressure inside, right? Let's just call that pressure 1, right? And this pressure is pushing on the wall to expand. But remember, there is also air particles outside. Let's call that pressure inside, PI. And let's just call this pressure outside, PO. And that pressure outside pushes the containers, this wall to move that way. And remember, this is fixed, that's fixed. This is the only wall that kind of expands. So what happens is, you know, just like forces, if the pressure inside is equal to the pressure outside, then this will stay. If the pressure inside is bigger than the pressure outside, then obviously this wall would move backwards, expanding the volume. If the pressure outside is stronger than the pressure inside, then this would kind of shrink, because this would be stronger, so it would push the wall like that. Okay? Understand that. That is crucial. Now, what happens is this: when you have this and it has a pressure inside, that's the pressure of the gas. Remember that, again, the fact that it's stationary, that means the pressure inside of the gas is equal to the pressure outside, which is PO, and they are equal, right? And obviously you also have that volume, that is the volume, right? The thing is, when you kind of increase the temperature, that means these particles here, remember what's temperature? Temperature is how fast the particles are moving. So if you increase the temperatures inside, it means the particles will now be moving even faster. And if they are moving even faster, that means when they hit the wall, they would be more violent in hitting the wall. If it's more violent, that means more force is exerted on the wall over the same amount of area. And you see what I'm getting here? It means that the pressure inside will increase. Okay? And because the pressure inside increases and the pressure outside is still the same, guess what? This will win. The pressure outside will win. It will push the wall. The wall then expands. Right? So therefore, when you increase the temperature, the volume expands. Right? And when the volume expands, obviously the walls are now bigger, are farther apart. So the particles can now hit the walls, but less frequently. Okay, lagyo naman. They are farther apart. So if they are less frequently, the pressure inside decreases. And it decreases such that it will now be equal to the PO outside. So it stays there. Okay? So in reality, it's really a multi-step process. What really happens is this. First, the temperature increases. Because of the temperature increasing, the pressure inside kind of, the particles inside kind of move faster, hits the wall, and therefore the pressure increases. And if the pressure inside increases, it will overcome the pressure outside. So it will push this wall to move further, causing the volume to expand. But notice, if the volume expands, if the volume expands, that means the particles are now, the walls are farther away, so it now hits the walls less frequently. So what does that mean? The pressure drops. So it's really like that. But since you increase the pressure and then you drop the pressure also, it's as if this did not happen. Because it's like the temperature increases, temporarily the pressure increases, then the volume increases, but because the volume increases, the pressure decreases. But since you get the same increase and the same decrease for the pressure, it's as if this did not happen. It's as if this did not happen. So the effect is, when you increase the pressure, the temperature, the volume increased. Okay? Let's put some numbers. Let's put some numbers into it. So let's say at first the pressure is 1 atm. That's a pressure inside the container, 1 atm. And obviously the pressure outside is also 1 atm. Right? So what happens is when you, and the temperature is, let's say 300 Kelvin, then the volume is 3 liters. Right? So what happens is when you increase the temperature, let's say you made it 400 Kelvin, what that means is the particles inside would be faster. If they are faster, they hit the walls more violently, more force. So therefore, the pressure temporarily, take note, temporarily increases to 2 atm. And because this is now 2 atm, guess what? The pressure inside is now stronger than the pressure outside. So it will push on the wall. So this wall will kind of expand. And if the wall expands, that means this increases. It becomes 6 liters. Right? But when the volume increases, that means now the walls are farther apart. So even if the particles inside are faster moving, because they are now further apart, it will now hit the walls less frequently. So less frequently, meaning this 2 atm will become smaller and smaller and smaller. And guess what? It will return to 1 atm. It will return to 1 atm. And because it's 1 atm inside and 1 atm outside, this volume now stops expanding. It will now be there. So you see, temporarily that pressure increased, but it also decreased. So the effect is, it's as if it's only the temperature and volume that really changed. And it's as if the pressure did not change. But in reality, if you really kind of conceptualize about it, the pressure needs to temporarily rise so that the volume increases. And then it will have to drop again to the original number, so that we can say that it's as if when the temperature increased, the volume decreased. The volume also increased. And when the temperature decreased, the volume also increases. Now let's take the second scenario, which is, what if the temperature is decreased? So if the pressure inside is 1 atm and the temperature is a 400 Kelvin and the volume is 6 liters. So again, originally you have 1 atm inside, and again this walls here are fixed. Only this wall is movable, and the pressure outside is 1 atm. And remember, when you say pressure, we mean pressure of the gas, so we mean pressure inside, not outside. Now, if you decrease the temperature, right? If you decrease the temperature, let's say from 400, you decrease it to 300. What happens? What happens is the particles inside will be moving less, right? You will be moving slower. If they are moving slower, that means they hit on the walls less violently, less force, less pressure. So what happens? This, ladies and gentlemen, drops into 0.5. This drops into 0.5 atm because the particles are now do not exert as much force as they did when it was 400 degrees Celsius. So if this is if this is now 0.5 atm, guess what? The pressure outside wins. So therefore, this wall will be pushed inside. So this will shrink like this. Right? So now the volume shrinks to 3 liters. But guess what? When the volume shrinks to 3 liters, the walls are now closer to each other. So even if the particles are now moving slower, it can now hit the walls more frequently because they can now travel at the walls are now closer to each other. So they can now travel easily between the walls and hit the walls more frequently. So what does that mean if they hit the wall more frequently? Yes, they will be hitting the wall at a less violent way because the temperature has now decreased, but they will be hitting it. They will be hitting it more frequently. So what happens? This pressure increases back to 1 atm. So even if the pressure temporarily dropped to 0.5 atm, it now went back to 1 atm again. So again, it's as if the pressure decreased to 0.5, causing the volume to decrease, but then it went back to 1 atm again. So again, if you take the summary, it's as if the pressure did not change. It's only that the temperature dropped, and so the volume also dropped. But again, in reality, you kind of have to change the pressure temporarily so that you decrease the volume. But that's the idea. That's how you kind of conceptually think about why the Charles's law works from the context of how we understand what temperature is, what volume is, from the context of kinetic molecular theory.